Okay, in this video I'm going to show you how to solve a ideal gas free expansion problem. In this problem we have a insulated rigid tank that's divided into two equal parts by a partition. And initially one part contains 12 kilomoles of a ideal gas at 330 kilopascal and 50 degrees Celsius. Now the partition is removed and then gas fills the entire tank. We need to determine the total entropy change during this process. Okay, so let's first imagine this process. We have a rigid tank, and then the rigid tank has a divider or partition in the middle. This is the division, and then you have ideal gas occupying 1/2 of this rigid tank. And we don't know what this ideal gas is. And we know it's 330 kilopascal and 50 degrees Celsius. And also it's 12 mole, so it's 12 kilomoles. And this is the beginning. And at the end, what happens is the partition is removed. So the partition is gone now. The ideal gas occupies the entire rigid tank. We don't know what the pressure is, so P2 is unknown, T2 is unknown, and we certainly know that the mass of conservation should be followed. Let's see. The mass of the conservation principle should be followed. Let me correct this. This 12 kilomoles. Okay, mass of conservation applies. How do we define the system? We define the system as such. Initial system is this. The initial system is a ideal gas system, and this big. And the final system, the system finally becomes bigger in volume, but mass is the same. It's the same system, not the same control, the same closed system, the same bunch of molecules, the same 12 kilomoles of molecules of a ideal gas. But there's a free expansion of ideal gas in this process, and we know free expansion is one of the irreversible processes, and this irreversible. And we also know this rigid tank is well insulated, so there's no heat transfer in this process. There's no heat transfer. So this closed system undergoes a free expansion, adiabatic free expansion process, and its volume increases by a factor of 2. So the question is, what is delta S? Delta S of the system. What is the system's entropy change in this process? Now remember, this is an ideal gas. Now search your toolbox and see what tools do you have in your collection that you can use to solve this problem. Let me get my equation sheet, which is my tool or my toolbox. I'll pause here and I'll get the equation sheet. Okay, here I have my equation sheet, and I found this entropy change equation. There are several entropy change equations. Now this is the entropy change equation. These are the entropy change equations. The first two are only applicable to reversible processes. Now the third equation, this equation that I have highlighted in yellow, this equation is a entropy change equation for ideal gas systems, and it's applicable to any process. So any process, if you know the beginning and or if you know the if you know the condition of the system, if you know the condition of the process, if you know the nature of the process, and you can use this equation to calculate the the entropy change of the system. Okay, so let me just copy this equation to my problem sheet. Okay, now I have copied this equation for ideal gases. The entropy change in the process can be written in such a way. So the entropy change involves two parts. One part is due to the temperature change of the system. The other part is due to the pressure change of the system. Now, this is a free expansion process, so it's not really a quasi-equilibrium process. So we may not know how exactly the process, how we cannot mathematically describe the change of all the properties in a well-defined way for this free expansion process. However, we can still assume that there is a way that you can there's an equivalent way you can move the system from the initial condition occupying half the rigid tank to the second condition. Let's just do some analysis of the entropy change equation first. Okay, we need to know how. Let's make some assumption first. If we assume if C sub P is constant, then we can simplify this equation with the equation becomes S minus S1 minus S2 becomes it is equal to C sub P is a constant integrated by integrated over this T, and then you can see it'll be log T sub 2 over T sub 1 minus R log P sub 2 over P sub 1. Now, it's natural log of the two ratios, temperature ratio and the pressure ratio. This capital R here is the gas constant of the ideal gas, and we need to make some changes to this equation in a moment. But let's just see how we can get T and the pressure and temperature changes of this process. Okay. So it's a ideal gas, and the ideal gas is free expansion in a rigid tank. We don't know what's the final pressure. We don't know what's the final temperature. We know it's a closed system that does this. What we need to do is a energy conservation analysis of this process. Okay, in a free expansion process. In this free expansion process, the key thing that we need to recognize is that the system doesn't do any work in this process. It pushes against a vacuum. So there's no effort, there's no need for the system to make an effort. It pushes against nothing. And then when it reaches the wall of the rigid tank, it hits the wall and it bounces back. And then after a few moments of back and forth, the system settles to its new equilibrium. So in this free expansion process, there's no work done. The system does not do any work. That's one key thing to recognize. Okay, now let's take a look at the system's energy conservation in this process. Energy conservation in this process. Delta E system is equal to E in, energy into the system, minus energy out of the system. Okay, what's coming into the systems in terms of energy? Nothing, because this system, the rigid tank is well insulated, so this is a 0. What does the system do work to the surroundings? No, it doesn't, because it pushes against nothing and doesn't do any work. And there's no heat transfer out of the system to the surroundings either. So E out is also 0. Now, what do we consider for the system's energy? Do we consider internal energy, potential energy, kinetic energy, or just one of them? Now, this is a system. Looking at the system, the schematic I drew, you have a system that sits there in the beginning and then sits there at the end. So the kinetic energy change of the system should be 0. And if this thing happens with no significant elevation change, the potential energy change of the system is also 0. So the only change we need to consider for the energy system is the system's internal energy. So delta U system is 0, and that's a very important recognition. Remember, this is an ideal gas, and the ideal gas internal energy is a function of temperature only. Is function of temperature only. Okay, so if the system's internal energy change is 0, then T2 is equal to T1, which is 323 Kelvin. Okay, so that's a very important thing to recognize. Now we know the system's temperature remains constant, and the system's volume increases by a factor of 2. So then, because volume 2 is equal to twice volume 1, and the system's pressure should reduce by a factor of 2. Okay, so now we have the ratio of the two ratios, T1 over T2 over T1 and P2 over P1. We need to make some changes to this equation. Remember, this R is equal to the universal gas constant R sub U divided by the molecular mass of the ideal gas. Now I'll pause for a moment. I'll write the new equation. All right, here I have rewritten the equation. Now, recognizing that T2 is equal to T1, so this term becomes 0, and we only need to consider the pressure change caused the entropy change. Also recognize this. Okay. The gas constant for a particular gas is equal to the universal gas constant divided by the molecular mass of the ideal gas. Now we can write the capital delta S, the extensive property entropy change for the system, which is capital S2 minus capital S1, and that's equal to the mass of the system multiplied by the lowercase delta S. Which is this equation. Okay, this equation comes over here and multiplied by the mass of the system. Now let's recognize that the gas constant is equal to this ratio, and we realize the mass m over capital M is equal to 12 kilomole here, kilomoles for this problem. So, and then we have this final result. This result is negative 12 kilomoles multiplied by the universal gas constant, which is 8.314 kilojoule per kilomole per K, multiplied by this, and we know P2 over P1 is 1/2. Okay, so now you can plug in these numbers into your calculator, and you can verify, see if the result is this 69 okay, 69.2 kilojoule per K. Alright, so because this is a gas-free expansion process and it happened in an adiabatic way, so this is essentially this is an isolated system because it's isolated from the surroundings. It doesn't have a work interaction with the surroundings. It doesn't have a heat transfer interactions with the surroundings. So anything that happens, any process that goes on for this system, which is isolated, can only lead to entropy increase, or if it's an isentropic process, then the system's entropy would remain constant. But in this case, it's adiabatic, but non-reversible. It's irreversible. So the process leads to entropy increase.